Hi, welcome everyone to our seminar. We are happy to have Bobby Kleinberg from Cornell. And if you heard the last few minutes, he will not talk about COVID in Cornell, but actually he'll tell us about work on total search problems beyond NP in the hierarchy. Anyway, so he'll explain everything.
Thanks, Avi, and thanks everybody for coming. So yeah, I'm going to be presenting this as a virtual whiteboard talk today, and please stop me anytime if you have any questions. I want to tell you about some new complexity classes that Christos Papadimitriou and I and two very bright Columbia grad students, Oliver Korten and Dan Mitropolsky, have been exploring. And okay, so in general, what is a search problem? A search problem is any computational problem where you're given an input string X, and you need to find a string Y such that some logical formula phi of xy holds. And when phi can be computed in polynomial time, this defines the complexity class FNP, which stands for functional NP. The decisional version of NP, of course, asks whether there exists a Y such that phi of xy holds. Here we're assuming that the desired output size is bounded by polynomial in N. So FNP is just a natural search analog of the decision problems encoded by NP. A typical NP problem is something like, given a graph and a number k, does it have a clique of size k? The search version of that is find a clique of size k if one exists. And so this involves computing partial functions. When it's easy to verify that some y is the output of the function. For many interesting classes of problems, and this is a total function. So we say a problem is in TFNP. If it's in FNP, and for every input, there exists a Y such that phi of xy holds. Okay, so let me just give you one illustrative example for now. I'll delve into more examples in a second. We can say that the input X encodes a circuit that maps integers in the range 1 through n plus 1 to the range 1 through n. And the search problem is to find I don't know why my whiteboard did that. find a pair of numbers n1 and n2 such that C of n1 equals C of n2. The pigeonhole principle guarantees that there is such a, that n1 is not equal to n2. The pigeonhole principle guarantees that there exists such a pair, but can you find a collision given just a description of the circuit that computes the function in which you need to find the collision? In this definition, I've been slightly sloppy and not said what I mean by an input string encoding a circuit that maps one set of integers to another one. So circuits are usually thought of as mapping an n tuple of binary bits to some m tuple of bits. So what does it mean that a circuit maps n plus 1, which might not be a power of 2, down to n? I'm going to standardize on the following interpretation. This means that C has ceiling log n plus 1 input wires. And at least ceiling log n output wires. And if you evaluate C on some input, and interpret it as a binary number, and that number exceeds capital N, then we'll just interpret C of little n equals capital N in that case. Okay, so in other words, I can, even if a circuit is mapping a domain whose size is 1 power of 2 to a domain whose size is another power of 2, I can always just truncate the range of the circuit down to any integer range that's not a power of 2 by saying numbers outside the range map to the largest element of the range. Okay, so what does the complexity landscape of total search problems look like? We've got
maybe Bobby.
Yeah.
Yeah, just to say that, for those that maybe all these bit lengths are confusing. Just to relate this example to the definition, first of all, it's very easy to check if two n1 and n2 satisfy this collision property to anyone who has the circuit, because it just evaluates it. And the other is that in this setting, I think to me it's always surprising that the most basic combinatorial principle, which is the pigeonhole principle, is really difficult. We don't know how to. Yeah, we don't know.
It's difficult, but it's difficult, but only because we're trying to find a collision in a function with an enormous domain.
Yeah.
Where the function is encoded very succinctly. So yeah, this is probably actually a good time for me to introduce this notion of.
Some people attribute to this phenomena exactly the conjecture that P is different than NP. I mean, that finding a hard function is a difficult problem, because most problems are hard, but so if you just map all functions to small circuits, there'll be many. The opposite of the pigeonhole principle says that you expect that almost every function is hard, but finding one, which is like this pigeonhole principle search problem, is hard. So we have a hard time finding hard functions and proving that P is different than P.
Yes. The opposite of the pigeonhole principle will play a starring role in this talk, and the observation that Avi made will actually reemerge in the natural course of things. Okay, so the complexity class of this problem I was just talking about, finding a collision in a circuit when collisions are guaranteed by the Pigeonhole Principle. This is called PPP for Polynomial Pigeonhole Principle. So the first P refers to the fact that the circuit encoding the function has to be of polynomial size. And it's one of a few interesting subclasses of TFNP, which are organized into a containment diagram that people often draw. And okay, and down here, we finally get functions that can be computed in polynomial time. So what's all this other clutter in the middle? These are different classes of total search problems corresponding to non-constructive existence proof principles in mathematics. So the pigeonhole principle is often used in non-constructive proofs to show that some object exists when we don't have a direct algorithmic way of describing or constructing it. But some other non-constructive proofs use the local search principle. Okay, so this is the principle that every function on a finite graph
please
has a local optimum.
Don't write too small, Bobby.
Oh, yes. Okay. Thanks for telling me. I'll write the next ones larger. Let's see. PPA stands for the principle that if a graph has an odd degree vertex, if a finite graph has an odd degree vertex, it must have at least two of them. And so I'll skip what PPAD and CLS are, maybe. But okay, each of these principles for proving existence theorems can be encoded as a computational problem of the same variety as the one that I did up here for the pigeonhole principle. That is, each of these has a natural encoding as a search problem whose input contains a description of a circuit or algorithm for computing something. So for example, the complete problem for the local search class, PLS, has an input that encodes two circuits, C1 and C2, computing functions called next and potential. And the search problem is find an X such that potential of X is less than or equal to potential of next of X. So the picture is that, Avi, go ahead. The picture is that these two circuits implicitly define a directed graph in which every vertex has an outgoing edge. Oh, sorry, nobody has two outgoing edges. I'm drawing it as if it is tree-like, but it doesn't have to be tree-like. Okay, so the C1 defines the arrows in this diagram. C2 defines a number at every node. And we're trying to find any local minimum, a point at which the value written there is less than or equal to the value at the node that is being pointed to. And you know, if we, the trouble is, because the graph has 2 to the n many vertices, and its structure is just implicitly and succinctly encoded by these circuits that have n input wires. The trivial algorithm of enumerating the entire vertex set of the graph, starting at one vertex and following forward arrows until I come to a local optimum, potentially takes exponentially long. And so PLS is the search problem that asks you to see if you can find the local optimum without doing the naive path following method. Avi, was there something you wanted to say?
No, yeah, you said it.
All right, great. One of the reasons that these complexity classes are interesting and influential is that they not only contain these sort of succinctly encoded meta-computational problems that involve reasoning about large functions encoded by small circuits, but they also contain natural combinatorial problems that don't require interpreting the problem input as a description of a computation. So for example, PLS is the complexity class of finding a Nash equilibrium of a potential game. If you don't know the terms potential game or Nash equilibrium, don't worry. I'm not going to be using that in this talk. I just wanted to give you examples of mathematically natural problems that belong to these classes. PPA contains problems where the proof that a solution exists has a topological nature. So there's a problem in PPA that's sort of a finitary encoding of the Borsuk-Ulam theorem. Some of you may have seen necklace splitting theorems that have topological proofs. So these are theorems where you have a ring of colored beads and you want to divide it into a certain prescribed number of arcs that have prescribed constraints on the number of beads of each color in each arc. PPP, the Pigeonhole Principle class, contains problems like lattice problems derived from Minkowski's theorem. So Minkowski's theorem is a very basic result in lattice theory that says if you have a centrally symmetric convex set of sufficiently large volume and a lattice of sufficiently small, whose fundamental domain has sufficiently small volume, then the convex set must contain a non-zero lattice point. The standard proof is a pigeonhole principle argument, and so the complexity of finding a non-zero lattice point in a convex set naturally belongs to PPP. And in all of these cases, the problems that I've written down here have been shown NP complete, have been shown complete for the respective classes. Oh, PPAD, I didn't talk about that. But that is the complexity class of finding fixed points of continuous functions whose existence is guaranteed by the Brouwer fixed point theorem. It's also the complexity of finding a Nash equilibrium of a bimatrix game, you know, two-player, non-zero sum game. So all of these subclasses of TFNP have natural complete problems. I should tell you, by the way, an important part of the story, and the reason that people focus so much on these restricted subclasses of TFNP, rather than the big kahuna TFNP itself, is that TFNP is believed not to have complete problems. That's not quite a theorem, but for example, there are oracles relative to which TFNP has no complete problem. And I actually am not an expert who could tell you the reason for this belief, but I have been told by Christos, who's the expert, that essentially everybody who works on total search problems believes that TFNP does not have a complete problem. So, you know, unlike NP, where the main organizing principle for understanding problems in NP is completeness, and the fact that almost all the problems we think about in this space are in one giant computational equivalence class of NP complete problems, within total search problems, there seems to be a much more refined and subtle relationship between problems, that they're not computationally equivalent to one another, but one can still find several fairly large computationally distinct equivalence classes of problems inside TFNP, none of which is complete for the entire class. So this is the way the complexity landscape inside TFNP has come to be understood. Another sign of how total search problem complexity is more ill understood than decision problem complexity is, here are some very natural total search problems that we still don't know if they belong to any of the classes in this diagram, other than the topmost one, TFNP. So where do these fit in? The first one is factoring. Okay, so in this problem, I give you an n-bit integer in binary, and you are supposed to output its prime factorization. That's clearly a total function problem because every integer can be factored into primes. So what's known as of now is that this is in randomized PPP intersect randomized PPA. In other words, if you have an oracle for solving the pigeonhole principle problem, or you have an oracle for solving the PPA problem, given an odd degree vertex in a finite graph, find another odd degree vertex, then there are randomized reductions from factoring to either of those problems. That's a result of Jarabek, 2015. While we're sticking with number theory, here's another very natural total search problem whose complexity status is not understood. Bertrand Chebyshev. Okay, so this is given the binary representation of a large number n. Find a prime between n and 2n. You've probably heard of the theorem that a prime always exists in that range. So what can we say about the, so therefore it's a total search problem. What can we say about its complexity? The only thing that I know to say about its complexity, well, okay, right. Two things. First, It's in TFNP because if I propose a prime number between n and 2n, we do have deterministic algorithms to test that that number is actually prime. So it's easy to verify a witness for this problem. And it's also in FP/poly. This is functions that can be computed in polynomial time with a polynomial size advice string. And the reason for that is very simple. So let's define P sub n to be the smallest prime number greater than square root of 2 to the n. Okay, so for numbers n that can be written in little n binary digits, one of the numbers P sub 2n, P sub 2n plus 1, right? Like if you look at the numeric range from 2 to the n up to 2 to the n plus 2, this is partitioned into 4 subintervals, each of which is a square root of 2 ratio between its two endpoints. And so P2n is in this interval somewhere, P2n plus 1 is there, and so on. My list of 4 primes contains an exemplar from each of these intervals. And meanwhile, if I plot n and 2n in this diagram, one of these square root of 2 intervals must be completely contained between n and 2n. And so that means that I'm assured that at least that one of the 4 primes on the list must satisfy the problem. So that says, if you tell me that the input consists of little n bits, there's a list of 4 primes that I can write down, each either n or n plus 1 bits in length, that contains a valid solution. And then you just need to run deterministic finality checking to, sorry, no, it's even easier than that. You just need to do bounds checking to see which one is in the range between n and 2n. So this sequence of 4 primes is the advice string that puts the problem in FP/poly. Incidentally, to introduce a theme that's going to echo a little later in the talk, this shows that in some sense, Bertrand Chebyshev is a sparse problem. Which is to say, although the input to the problem ostensibly consists of n binary digits, the digits do not really matter so much for solving the problem. If I just told you the input length, if I just told you that the input is n digits long, but I don't tell you what the binary digits are, that's already basically enough information to allow you to solve the search problem. So that's quite different from these other ones where the, like factoring, if I just tell you that a number is n bits long, that gives you almost no information about its prime factors. Okay, let me give you the third quintessential example of a problem that is in TFNP, but we don't know where to put it in this complexity hierarchy. Ramsey. So in this problem, we're given a graph with 4 to the n vertices whose adjacency relation is encoded succinctly by a small circuit, a circuit C of size polynomial in n. And we're supposed to output a clique or independent set of size n. The finite Ramsey theorem guarantees the existence of such a set. And if someone gives you a candidate clique or independent set of size n, it's easy to verify that it is a clique or independent set by just calling the circuit n squared times to find the adjacency of every pair of vertices in the proposed set. But we don't know how to solve this in polynomial time using an oracle for any of the other total search problems in this diagram up here. So there's still quite a bit of intrigue in classifying the complexity of particular interesting computational problems according to where they sit inside TFNP. But the question that I'm going to focus on in this talk instead is what total search problems lie beyond TFNP. And since I was stressing this perspective that says complexity classes that are in TFNP but not in FP correspond to general non-constructive methods for proving existence of mathematical objects, then a conceptual question relating to this complexity question that I just wrote down is what types of non-constructive existence proofs are there besides the ones detailed above. Okay, so I've been talking about topological methods, the pigeonhole principle, the principle that every function on a finite graph has a local optimum. Where else do we see fundamentally different non-constructive methods for proving that certain objects exist? Well, in my opinion, I have not gotten to the most important and widespread non-constructive existence technique in combinatorics, namely the probabilistic method. Which says if we can show that for all x, the probability that a random y satisfies phi of xy is greater than 0, then we know such a y must exist.
Well, the
And this is
Pigeonhole principle is, in a sense, a special case, I guess.
yes, I accept that. The Pigeonhole principle. Yes.
Okay, so Emil Jedrzejbek has some work also applying some sort of probabilistic method in some theory in proof complexity.
Yeah, Yuval, I missed the name that you said at the beginning of that.
It's the one you call Jedrzejbek, but it's pronounced more like Jedrzejbek.
Oh, right. Yeah, in fact, there's an even older paper by Alyachnovich. Avi is one of the authors. I'm forgetting who all the authors are. That was also about sort of proof complexity of pseudorandom generators.
Yeah, there are many connections to proof complexity. I don't want to. We can discuss it later. There are questions. Yeah, of course, Yuval is right. Yeah, I was just wondering whether you would call the Pigeonhole principle a probabilistic method or not. It seems to me that it is, but probably you have more sophisticated examples.
So you're saying the Pigeonhole principle can be summarized by a random pair of inputs have positive probability of colliding.
Yes.
Yeah, I was thinking whether to debate you on that or not. Since you brought it up a second time, let me debate you on that. If you asked me how to prove that collision probability is positive, I would invoke the Pigeonhole principle to say, by the Pigeonhole principle, we know that there is a pair that collides. So a distribution that has full support that puts positive probability on every pair has positive collision probability. I guess, so in that sense, it's a circular argument way of proving the Pigeonhole principle the way that I would do it. There might be, like using Cauchy-Schwarz, you might be able to show positive collision probability in a way that does not, at least on its face, invoke the Pigeonhole principle. Avi, go ahead.
It's a double summation, but it doesn't matter. I mean, let's see your example.
Yeah. So my example is sort of the reverse of the Pigeonhole principle. So the reverse of the Pigeonhole principle says if F is a mapping from n elements to n+1 elements, then there exists a y such that for all x, f of x is not equal to y. Okay, so the probabilistic method proof of this says pick a random y. There are n inputs x, each has 1/n+1 probability of hitting y. So the combined probability of those events is less than 1, so there must be a y that is not hit by any x. It's overkill to call this the probabilistic method. It's really a very, more basically, it's a counting argument. But this style of counting argument is ubiquitous in combinatorics and complexity theory. Earlier in this talk, Avi gave the prime example, which is we know that functions which are hard to compute must exist. How do we know? Because we can count the number of polynomial-sized circuits with n input wires. We can count the number of functions on n inputs. And the second number is much larger than the first. So let's see how to interpret that as an invocation of the reverse Pigeonhole principle. you could think of the function truth table. Okay, so this is a function from size Boolean circuits of size S with n inputs to functions from 0, 1 to the n to 0, 1. So how many of each are there? There's about 2 to the power s log n of these. Sorry, what am I saying? S log s. And there's 2 to the n many of these. So therefore, if s log s is greater than 2 to the n, there's a function that has no circuit of size s. The trouble is we just don't know how to find it. Okay, so the complete problem that encodes this reverse of the pigeonhole principle, we call it PEPP for polynomial excluded pigeonhole principle. And it says given circuit C representing a function from n to n plus 1, where C has little n input wires, ceiling of log n if you want to be precise. Find some y in square bracket n plus 1, which is not in the range of C. And the basic difference, this is not a TFNP problem, because if I tell you the answer y, to verify that y is the correct answer, you need to check the validity of the logical formula for all z, f of z, c of z not equal to y. Okay, so that's not a polynomial computation. It's a co-NP problem. And so it's natural to call this class TF sigma 2 rather than TFNP. So a total search problem is in TF sigma 2 if total search problems of the form given X, find Y such that for all Z, phi of X, Y, Z. And we can build a bigger hierarchy by allowing more quantifier alternations. So TF sigma 3 would be find Y such that there exists a Z1 for all Z2, phi of XY, Z1, Z2. And in general, TF sigma K could be defined for any finite K similarly. The question, of course, is does this hierarchy contain interesting problems? So at the second level of the hierarchy, we have this excluded pigeonhole problem, which is very interesting because in particular, it encodes complexity theory's quest to find a Boolean function that has no small circuits. And actually, to say a bit more about that, that problem is a unary problem, by which I mean the standard problem that circuit complexity focuses on is given a particular circuit size, find a function that cannot be, given a number of input bits, find a function on n-bit inputs that cannot be computed by small circuits. So no circuit with fewer than n to the 100 gates. Okay, so the input to that problem, as typically conceived, is n, the number of input bits. Okay, but and there are many other interesting probabilistic proofs of existence that are very relevant to complexity theory that also have this unary character. Okay, so other existence theorems with probabilistic proofs. We have, for example, given a function C, mapping delta n bits to n bits, there is a string y in 0, 1 to the n that is far from the range of C in Hamming distance. How far? At least R of delta times n. For some function R that maps positive constants to positive constants. How do we figure out what this radius is? You use the union bound. We know that the size of a Hamming ball of radius delta n.
Radius Rn.
Oh yeah, radius Rn. It has about 2 to the binary entropy of R times n elements. So if H2 of R plus delta is less than 1, then we have a mapping from 0, 1 to the delta n cross 0, 1 to the H2 of R times n into 0, 1 to the n. This is x comma y maps to the encoding of x plus y. Yeah, sorry, actually, y should take values in the Hamming ball of radius Rn. And searching for a point which is far in Hamming distance from this code is equivalent to searching for an element of this set that's not in the range of this function. So it's another instance of the PEPP problem. Other examples, rigid matrices. I won't. So rigid matrix is a matrix of full rank that cannot be made low rank by changing a small number of entries in each row. And it's easy to show using the probabilistic method that a random matrix has this property. And people have been trying for decades to find explicit constructions, but we're very, very far from constructions that have the optimal parameters that are known to be possible using the probabilistic method. Okay, so that probabilistic method proof encodes a PEPP problem where I take low rank matrices cross sparse matrices. I have the addition map that maps them into n by n matrices, and I'm looking for something that's not in the range of that function. And if you give me an oracle for solving PEPP, then it can easily be used to find rigid matrices. A lot of these applications of the union bound correspond to probabilistic proofs with constant success probability. Okay, and so to encode the complexity of these kind of generous union bound proofs, we also have a subclass APEPP where the function, instead of mapping n to n plus 1, maps n to 2n. This is an important class of problems because it contains most of the simple applications of the probabilistic method. So it's very interesting to know what's the complexity of solving this problem. But it has a very irritating complexity status, which is it's probably easier to find such a y than to verify that it's a correct solution once found. Okay, the reason for that is there's a trivial randomized algorithm that produces a list of candidate solutions of polynomial length that, with very high probability, contains a correct solution. You just don't know which one it is. If you just keep guessing elements of the range at random, then it only takes a constant number of guesses in expectation to get one that works. And if you want, inverse exponential probability of failing to contain a solution on your list, then instead of guessing just once, guess polynomial in n number of times. Okay, so one way of expressing this is that AP EPP is contained in FZPP to the NP. Okay, what does this alphabet soup mean? So this is randomized algorithms that always succeed. And they run in expected polynomial time. And the superscript NP means that as the algorithm runs, it's allowed to consult an oracle for an NP complete problem such as SAT. And if you have those two capabilities, randomization and a SAT oracle, then the way that you solve AP EPP problems is you keep guessing output strings y. You run a while loop where you guess a random y. You ask the SAT oracle, is there an x that maps to this y? That's a satisfiability problem. So the oracle tells you yes or no. If it says yes, then you draw another random y. The first time the oracle says no, then you know that you have a correct solution. Okay, so and if you don't like randomization, the standard argument of Edelman for converting randomization to advice strings shows this is also in FP to the NP with polynomial advice. So that means that in some sense, AP EPP is probably easier than the problems in TFNP. It's just not easy to verify when you have a correct solution to one of them. It's 12:15, so I think the seminar is supposed to run for 1 hour, Avi? I think you're muted. Yeah, you're still muted, Avi.
You didn't hear me. Yeah, sorry.
No.
Yeah, I said, well, you could have guessed it yourself from our interaction before the talk. So why don't you give us like a 5 to 10 minute summary, or whatever you want to talk about, the questions you want to ask, or what's
yes, very good
understanding of this and where we should go.
Great. So at the start of the talk, I gave you a roadmap of what's known about the TFNP and its subclasses. And the vital features were it contains interesting problems that are probably not in P. It probably doesn't have a complete problem. The interesting problems in TFNP can be grouped into subclasses of computationally equivalent problems that correspond to interesting proof principles. And for all of these subclasses, we know a natural problem that is complete. So let me relate that to what I think what I hope to have shown you about the higher levels of the hierarchy. Okay, so inside TF sigma 2, I gave you at least one example of a subclass that I would argue contains interesting problems. And in fact, a subclass deeper within it that contains most of the interesting problems in the first one. What I didn't show you, and we don't have a good candidate yet, is we don't know natural complete problems for PEP and APEP. So all of the complete problems that we know, the input encodes a circuit. Whereas there are nice combinatorial problems like finding, I give you a partially completed matrix and I ask you to fill it in so that the full matrix is rigid. It's easy to see that that problem is in APEP. It's definitely not obvious that it's complete. I would actually be surprised if that were a complete problem for APEP, but it would be, we would like eventually to discover a complete problem for one of both of these classes that has that combinatorial kind of character, that the input is not a description of a computation, but it's a description of an actual mathematical object that one would like to construct absent the computational context. Okay, what else do I want to tell you? I didn't get a chance to show you, but it's easy to see all of FNP is inside of PEPP. So this class really is bigger than TFNP. And above TF sigma 2, we have TF sigma 3, TF sigma 4, etc. So you might wonder, are there also interesting problems up in these more stratospheric levels of the hierarchy? So in our paper, we show two interesting examples of problems in TF sigma 3. One of them is called Shattering, and it encodes the famous Sauer-Schallack lemma that if you have, a large collection of sets, then it must have high VC dimension. And also in here, there's another interesting problem called King that encodes the principle that in a tournament, there must be one vertex that can reach every other by a path of length at most 2. Above TF sigma 3, we don't even have candidates for sort of natural computational problems. There are interesting questions about the relations between different levels of the hierarchy. But maybe I should save that for later if someone wants to ask me. So thanks, Avi, for inviting me to give this talk. I had a wonderful time presenting this paper to you.
So I have a high-level question for you, Bobby.
Yeah.
So, by the way, that was a really nice talk. Somehow, when you talk, it feels like you're just talking to me. Somehow, that's.
Well, that's the nicest thing I've heard at the end of a Zoom lecture since I've been doing Zoom lectures. Thank you, Peter.
So, if you take all these classes and you strip off the computational aspects to it, it comes down to theorems.
Yes.
And these are all theorems of ZFC. And many of them have been studied by the likes of Steve Simpson and Harvey Friedman, doing reverse mathematics, trying to figure out which, weak subtheories of ZF are actually enough to prove these things, right?
Yes.
So I think you would get the same sort of hierarchical structure from that, or a similar hierarchical structure that you get from looking at the, I have no idea whether this is really the case, but
yeah.
Sorry, Bobby, you can answer.
Oh, no, I'm also curious to hear Avi's answer. So what I was going to say is there's a pretty recent paper of Goldberg and Papdimitriou that gets into relationships between proof theory and these total search problem complexity classes. And they create a meta recipe for defining total search complexity classes, where the input to the machine is you define a propositional proof system, and then you have a search problem where I give you a succinct encoding of proof of a contradiction within that system. And the search problem is find the wrong step. Because I derived a contradiction, if the proof system is consistent, you know that there must be a step in the proof that does not actually follow as claimed from earlier steps. So find the wrong step. Okay, and they show that all of the well-known TFNP classes can be represented as instantiating this paradigm for particular propositional proof systems.
Wow, that's a really nice idea. I like that.
But Avi, I was curious where you were going to go with Peter's question.
Yeah, no, this is maybe it's sort of a last step of a long series of investigations. I think that first of all, to what Bobby said in the very beginning, that unlike NP completeness, where we have for NP we classify everything nicely. For the question about separating NP and co-NP, we are much more in the dark, and there are various methods by which you can try to prove a theorem, basically, or if you wanted to show that NP was co-NP, you want a method, say, to certify that such a formula does not have a solution. And so in mathematics, like Peter was saying, I mean, there are lots of methods. They all fall in ZFC, or maybe almost everything we care about are in piano arithmetic even. But we want to understand or to classify which proofs belong to maybe a weaker theories. And so one major area within complexity theory is proof complexity, and there you study the power of restricted proof systems, restricted propositional proof systems, like resolution and similar ones, Frege, which are logical, where the reasoning is logical, like cutting planes, where the reasoning is geometric for integer programming, for example, like Null-Challenger for proving a system of polynomials are inconsistent, and so on. And these proof systems basically encode reasoning principles, and now a natural search question would be to find such a proof. I mean, what's the complexity of finding such a proof? And it's very natural that they both fit. Actually, after the major first paper on total functions of Papadimitriou, there was a really nice paper written by Tony Pitassi, Russell Impaliazzo, Steve Cook, and maybe someone else, Paul Beam, where they relate the two. I mean, they basically put this type of questions from the point of view of proof complexity and show that some of them fall naturally into non-proof systems, and maybe others don't. And there's lots of work that was done on this type of questions, understanding these search problems from the the proof complexity point of view. I mean, basically, finding an example of what Bobby just described is I'll give you an unsatisfiable formula. Find a clause. Sorry, I'll give you an unsatisfiable formula, and I'll give you an input. Find a clause which is violated. So this type of search problems are in fact addressed every day by SAT solvers. So it's and the various SAT solvers would search for this in different ways. And yeah, there are lots of connections. Maybe I shouldn't.
There's also there's a paper I was just.
One more thing. Let me just say one more thing. This is all in the propositional level, and Peter was talking about ZFC and so on. One person that has connected the two, and specifically to the question of P versus NP, is Sasha Razborov. He wanted to study the, maybe the question of P different than NP is just independent of set theory. That's a possibility. And one way to get at it is to prove that it is independent of some weak theory. And in fact, he proved such a result. And the proof of this result, it's some second order theory within piano arithmetic. And the way to prove this result is via propositional proof complexity. So it's well known by now that lower bounds in propositional proof complexity give independent results in the normal proof theory setting for some systems. So there are results proving some independence of P versus NP against some natural subclass of piano arithmetic.
Good, thank you very much. Yuval put some useful remarks in chat as well, so thank you, Yuval.
There's one more thing I wanted to. Oh, Yuval, go ahead.
Yeah, so another answer to Peter's question, there's bounded arithmetic. So these are fragments of piano arithmetic, which are, some of them are quite weak. And one of them is this theory APC, which is supposed to capture probabilistic arguments of the same form that Bobby described. So sounds pretty similar.
So I guess the one remaining thing I wanted to say in answer to Peter's question, there's, the star of the show in my talk was this excluded pigeonhole problem, which is you have a function that doesn't fill its entire range. How hard is it to find an element of the range that isn't hit by the function? So instead of thinking about that as a search problem, you could say, I have a function whose domain is smaller than its range. How hard is it to prove that a specific element of the range is not in the range of the function? We know that such elements must exist. Is it possible that you could have a pseudo-random function which fools the excluded pigeonhole principle in the sense that for every element of the range, there's no short proof that it's not in the range of the function? Sorry, for every element of the codomain, there's no short proof.
Codomain is what you mean.
Okay. So Avi and Misha Lechnovich and a couple other authors, I forget.
And Russell in Pagliazzi.
They have a paper where they construct pseudorandom functions with that property against certain weak proof systems.
Oh, cool.
More questions.
Proof complexity generator. Cool.
Anybody?
Yuval, thank you for all the pointers that you're putting into the chat window.
Good. So you think factoring
oh gosh,
is going to fall because it's not complete in any of these classes?
I'm exactly the wrong person to ask that question. Or maybe I'm exactly the right. I'm mostly an algorithm designer who took a very pleasant stroll into complexity theory with Christos and his students to work on this paper. But I look at a problem like factoring, and my mindset is there's probably efficient algorithm for it that we just haven't discovered yet. Or at least it's very hard for me to picture how we would embed a meta computational problem like one of these as an instance of factoring.
Okay.
And I think the fact that people keep discovering 2 to the n to the k algorithms for smaller values of k. I think did someone just get it down to 1/5 recently?
Yeah, I think the third is the only one provable, but even maybe half is the only one really provable, and 1/3 is what everybody believes the assumptions. But anyway, didn't mean to put you on the spot for that.
But I mean, it would be nice to at least see that factoring is deterministically reducible to one of these other more well understood classes. At present, we just have the randomized reductions.
Any other questions? All right, Bobby, thanks a lot.
Thank you so much for having me.